What's up, everybody? Welcome back. Today we are working on our virtual GPU, and today's topic is continuing on with memory mapping GPU memory straight to user space. So the idea here is, we have this like GPU that we've implemented, right? GPU. He's like really virtual, and he's not really very good. But he exists and he lives in this virtual machine called QEMU. We have extended QEMU, this like open source virtual machine, with a PCI device called Sphero GPU or something. I don't really remember. We are working towards implementing like an OpenGL driver for this thing. But in its current state, he can at the very least like display some stuff to the screen, right? So we have like in QEMU a little screen, and we can like draw a little smiley face here. And if we open up QEMU, here's a little smiley face, right? He's blinking really slow because of some details we'll get to in a second. But we have the ability to like draw stuff to the screen. We have a kernel driver for this thing, and we'll just call this like driver here. And he talks to this PCI card, and he issues calls to him to like, say, I want to put a pixel here, or like I want to clear the screen, I want to show this buffer, I want to allocate some GPU memory, stuff like that, right? And his job is to effectively expose this thing called like DRM, Direct Rendering Manager. His job is basically expose a DRM API to user space. User space, where applications normally run, right? So right now we have like kind of like two interfaces that work through this guy. There's like the DOM API, DOM, as well as like custom, I guess we'll call it. So the idea here is that if you want to display some text on the screen while you're booting your machine, there should be some minimal surface area of like an API that all GPUs implement. And that is just like put some pixels on the screen effectively is that API. Now, we've kind of got this working in the past through some other mechanisms, but we're working towards the idea of making that API work with GPU-backed memory, right? So we're gonna have like some buffer over here, and we wanna be able to like draw the smiley face into this buffer, but we wanna be able to do that from user space. And so what they do is they have like in this dumb set of commands, they have this thing that's like allocate dumb buffer. This is like a common Linux API, as well as map dumb buffer, right? What we did before was in like we allocated like basically this in kernel memory here, and we told the GPU where in like host memory this was. So because of like the PCI bus, he can just kind of like peek his eyeballs over here. You can look over here, you can look over here, you can look over here, right? And this worked okay for the initial implementation, because in this world, this looks like a contiguous buffer that we can map to user space very easily. But in reality, in physical memory, it's like split up into many chunks, right? Wherever like physical memory had room, it's where it put it, right? Which means that in the GPU side, when he's looking at this thing, he actually has to look here, then he has to look here, then he has to look here. And as we start like moving forwards with adding more GPU APIs, like the ability to like upload vertex buffers and like asking him to like implement like a clear command, now all of a sudden it makes more sense for our implementation of our like fake GPU to have all of the memory contiguous in his view, right? And so what we were working on is exposing a buffer that lives here over here. And so the like interface that we've come up with is PCI devices have these things called bars, base address register. And basically what they do, if I understand correctly, is they ask the bootloader, or maybe the kernel, not 100% sure there, to basically set up some memory mapped regions, or where if you talk to if you write at this address, the PCI device will pick it up, right? So you kind of like imagine you have like a PCI device, and it's got like memory regions that he's set up, right? And the bootloader will say like, okay, this is like at like address 100, this is at address 500, and this is at like address 700 or something, right? These get like mapped somewhere. And so then in the kernel, maybe the BIOS even, yeah, could be. Or maybe both. Maybe all three, maybe two of the three, right? Who knows? So what happens now is like now in the kernel, if I write to physical memory 0x500. Now my PCI card can handle that in whatever way it wants. So what we've done is we've kind of allocated one region that's like basically like a command register, like a command region where you put in like the command ID here, ID, and then you put in like args here, right? Args, matey. And what we've done is we've added a new command called map, which will take in a like source and destination essentially. So like we'll take in like object ID, as well as like where we want it to get mapped to, dest, I guess, and offset, probably something like this. And this will go into a second bar, which we have allocated to be like really, 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 really big, right? And this basically takes in like, this has like pages in it essentially, chunks of 4096, right? And we're basically saying from the kernel, we can ask the GPU to expose its own memory through this bar, but kind of like in like a mishmash of ways. So every time we try to write to this thing from user space, what happens is the kernel will go, well, okay, first we have to like call this function called mmap, right? Which says like, hey, give me a pointer. Give me a pointer that I can read and write to. And what happens is our kernel driver can implement this mmap call however it wants, right? And so what we have chosen to do is we've said, okay, well, when somebody tries to read and write to this thing, the kernel is going to go like, essentially he's going to segfault, right? He's going to be like, what the hell? Where is that, right? Because all we do is we say, hey, here's a bunch of memory that's like, 100 bytes long or something, right? But this doesn't actually point to anywhere physical. It's just like, it's kind of just there as like you could use this thing, but you don't know how yet. Then someone writes here and that like triggers like a page fault, right? The kernel goes, holy shit, I don't know where that actually lives in real memory. And so it calls our function in order to like figure that out, which means that in our function, we can call this mapping command and then return the address of one of these things and say, okay, when they write here, use this, essentially, right? That's what we've implemented so far. Now the problem is we haven't done kind of any of the management of this thing, right? So we have it right now so that every single mapping goes to the first slot, and we don't really track like eviction of this thing very well. At the end of last stream, this face did not show at all, and it's because we didn't handle eviction ever. So basically everything, this whole memory space got mapped to this, right? And so anytime you wrote anywhere, it would just write to like the last mapped thing. I found off stream this command that does exactly what we want. Sphero derv, and I think it's zap something. Zap VMA PTEs. Zap page table entries for this virtual memory A allocation, maybe? I don't know. But this is what we want. So now I've implemented that, but it's kind of like we're not tracking where things are correctly, and it's slow as fuck. Right, you can see this guy's like, you can barely see his eyes move. This is supposed to be running at like many FPS. He's not. So I think the plan for today is to try to fix our page fault handler so that we are like using as much of the PCI bar space as we can. We want to make sure that when pages are getting evicted, we are tracking those things correctly. Because right now we are basically just saying we have one mapped page for our entire driver. Really what we should, and we are assuming that mapped page is related to like this virtual memory allocation. That's not necessarily true. So we have to fix that. And I think that's probably pretty much it. I don't know. Then probably we can probably map a good chunk of the memory before we even like start running. Before any page faults happen, because if we have like 256 megabytes of space to work with and somebody tries to map like a 4K buffer, we can just do that up front so that we don't have to like tank the cost of page faults on writes. So that's the plan for today. We'll see where it ends up. It could go fast. It could go slow. Who knows? Apologies for the long intro, but I was yapping. So I think step one is to track the allocations correctly. We need to track these things. So our driver, presumably, needs to kind of have some sort of like bar mappings or something, right? And I don't really know what lives in this thing yet. But I guess we have 256 megabytes of PCI space to work with. I think that we got this wrong actually earlier, so I'm going to define this as like bar size for now. Because initially we set this as 256 times 1024 because we saw 256, but this is actually 256K, not 256M. So this should be 256M, not 256K. But I kind of want to start with where we're at right now. I think that somewhere when we tried to map this region, we must use that same number. So on our like driver initialization, we do PCI initialization, and here we said, oh, I see. We just mapped the resource start here, and we assume that anybody who's using this thing is using like, yeah, we've got like an implicit size here. So we're actually just allowing people to go off the edge. That's kind of funny. Okay, but this will change now. This will change now. So we, I guess, are going to say each mapping is going to be tracked here. So I guess if we're going page by page, we're going to have something that's like sphero num bar pages, which is going to be the size shifted right by page shift. Yeah. And then that should tell us, like, then we could just track those things, right? So we can say, like, I guess we want, like, a single mapping. Which is just going to be what? I guess we're probably going to store, like, my guess is that we can keep track of the VM area struct associated with this thing so that we can, when we try to zap it later, we know we can keep track of that. What was it? VM area. Hold on. Do you need to map freed pages? I don't think so. I'm more worried about the fact that I have to unmap pages to make room for new ones. Right? So if we use up the whole buffer space, we need to go like, oh, these, like, I need to put this thing in here. Which of these, like, million things should I evict? And I should, like, take one out and replace it with mine, and then say to whoever currently had that page mapped, be like, oh, no, you're unmapped again, which is what this zap call is for. So this is going to be, like, VM area struct. A little redundant struct here, but that's okay. Okay, so he's going to have a VMA, as well as the address range that he is working with. So probably like which page this is within the VMA, which I think that we call page offset. Like this. And our mappings are probably going to say that we have sphero num bar pages worth of these things, right? Right? Something like this. This is gonna be like mapped. So we'll say that like for each bar page, this tells us where it is mapped to in virtual memory. Yes. And I guess technically, this, we could map the same, we could map one bar page to multiple VMAs, right? If you have if you're like in process 1 saying like, I want to look at this hardware buffer, and in process 2 you want to look at the same hardware buffer, like technically that's possible, but we just won't support that for now. If that case comes up, we will just map that same page twice, right? So we'll be like in, I should stop this from just railing my CPU. There's no point in that running, right? So in this, what I'm talking about here is if you have like GPU memory that's contiguous in GPU land, then we have like the bar. You're gonna have like some object here mapped to like some location here, right? And then if you theoretically had like user space processes both want to look at the same thing, right? These could both be pointing to the same spot. But instead, what I'm going to do for now is I'm just going to like map this twice and then do it like this. And I think that kind of solves my problem for now. So, maybe we'll say bar pages like this, and then for each bar page we have this is like a VMA mapped page or something, right? Seems reasonable. Okay, then this allows us to track at the very least which things are allocated. I guess I might want these to be pointers so that I can write null. That kind of sucks though, so maybe we'll just say valid here. That's not great either, but it's fine. It's fine. Oh, we're supposed to be careful about like alignment here, right? In this language, things are just allocated in these things come in order. So like you want to do this first, then this, I think. Oh, it doesn't fucking matter. Okay. Now what? Let me think. Is this all we need? Presumably we want to keep track of like the order of usage of these things, right? Like can we track like which page was least recently used? I'm not actually sure we can track that, because if we map the pages and then just write into that memory, I don't think the kernel ever like intercepts those writes, right? Once the page is mapped, then it's like completely blind to us. So it's hard for us to know which page is most likely to be unused. Who can track that? What if we just left this bar mapping management up to user space? Right? So we say no, because like if I want to map like a really, really big buffer, bigger than the PCI bar space, it would be nice if that's just like automatically handled. So what like heuristic can we use? Can you observe the TLB? Does it know? Like, what does TLB stand for again? TLB stands for like translation look aside buffer. That sounds right. Is this like a thing we can look at? Unmaps or modifies the attributes of range of memories, blah, blah, blah. Because that would be cool. Is that worth it? I'm trying to decide how I want to do this. That'd be cool. That would definitely be cool, but I think complicated. At the very least, I would have to do some reading on how to do that, so I don't really want to start there. We could assume. What if we like base it off getting it wrong, right? So we can kind of like maybe assume nearby page. Assume last mapped page. Assume that the last map page is also last used, right? This is an invalid assumption, right? But if we get that wrong, we unmap the page, then immediately remap it, right? So like it's like kind of wrong, but it fixes itself, right? Now, we should be careful though, because imagine that from user space I'm going like I'm like looping over each thing, right? So I'm going doing something that's like right frame buffer, right? And I'm going like for int I equals 0, I is less than buff size, plus a I or something, right? And I'm doing like buff I is equal to thing, right? If we do this, then it's pretty clear that like things around what we are writing are like also interesting. So we might want to like add some heuristic for pages close by to most recently used page. Right? That kind of would make sense, but maybe we kind of leave this part for later, and let's just assume for now that we'll just do this. Fuck it, right? So we want to store somewhere the order, an ordered list of which page was last mapped. So like on mapping, we need to update something. So it's going to be like mapped page order. And we could do this as just like this. Like we could do like a, something like this, where each one of these is like the index of that page. But management of this thing sounds kind of expensive, right? This might be a rare case where I'm actually okay with a linked list, right? So with a linked list, we're gonna kind of be popping elements all over the place. Let's think about this for a second. If we did a linked list, we could go like list head. We could maybe keep track of list head, list tail. We push to list tail, pop from list head, and then every time a buffer is mapped, it would like end up at one side. It seems like actually this is a circular buffer, is what we're describing right now. Yeah, I guess like because we're not ever updating, we're never updating the we're never updating the usedness based off of anything but mapping, then the order is like static. Yeah, this is very circular buffery. I think drivers normally don't let you map more than 256 more megabytes of device memory. Usual solution is to use CPU memory mapping and then do CPU GPU copy. I just don't like the idea of that. It bothers me. Why copy? Because like why copy from user space into shared memory, then shared memory to the GPU when you could just copy it directly to the GPU? I'm sure there's good reasons, but I haven't discovered them yet. Is the main screensaver gone forever? Yeah, pretty much. I like the ball machine better. Yeah, so let's just do like a circular buffer. Does the kernel have one of these already? Circular buff. Looks like they just kind of roll it by hand, huh? Circular buffer. Oh, wait, okay, hold on. Circular buffers, core API. Linux provides a number of features that can be used to implement circular buffering. These are two sets of features. Convenience functions for determining information about power of two-size buffers. Memory barriers from the producer and consumer objects. What is a circular buffer? Head, tail. Measuring power of two buffers. Using memory barriers. No, doesn't really seem like what I want. Okay, fuck it. We'll just kind of roll it. We'll roll it by hand. One advantage is that DMA can be faster than straight PCIe writes, especially for large buffers. Less important for smaller things like command buffers. Also, DMA does not keep CPU busy. Oh, those are really good points. Yeah, that's a really good point. I didn't really consider the fact. No, well, let me think about that. Because doesn't. Okay, I think I'm seeing it. So, in your DMA case, you have PCI card kind of directly hooked up to the memory bus, like RAM. You also kind of have this like bar. The bars aren't really like going through here. This is kind of more like these things both go into the memory controller. Memory controller, or whatever the fuck it's called. MMIO or something. So, I guess it's kind of probably more like this, probably. Would be my guess. My guess would actually be it's like kind of like this. And then you have CPU here, is kind of what you're saying, right? Now, if I'm doing bar writes, that goes here to here, right? Which means that like, I think, which means that I'm essentially sending like PCI formatted messages in like some sort of like PCI packetized format this way. But which means that like I kind of have to eat the latency of the PCI card like handling that packet in some way, shape, or form, right? Where if I write to memory and then send one DMA command, it's like I write the memory through here, then send one command that says, could you copy this memory? And then we get some sort of like exchange that goes like this and then back, which frees up the CPU to do other stuff. That makes sense. So now I see it. But we're already committed. We're already committed to doing it this other way. So I will consider this in the future, but I do want to finish up this idea, and then maybe we could like compare those later. But I do understand why that's fucking stupid now. But it is what it is. Okay. So yes, also there's a performance benefit with PCI burst that can only be triggered with DMA. Okay, that makes sense. I guess these things need to be prefixed because we're in this like C language. And then let's figure out how to do this circular buffer thing. So we're gonna have like a head, tail, and data. Okay. Of what? This is just gonna be like UN32Ts. We have arrived. Yo, what's up, you guys? Bash Bunny, thank you for the raid. What's up, you guys? I hope you got a good stream over there. We are working on our virtual GPU. So, the intent here is that we are trying to understand one day what would be, we're trying to understand, one day we would like to make a GPU, right? And we're trying to understand, like, what does a GPU actually do? And because we are incapable of reading, we figure the best way for us to understand, like, the split between hardware and software responsibilities is just to implement the whole stack, and then we'll have to get it, right? There's no choice. So we have kind of got, let's see if our diagram's up here. Did we lose it? Here. We have a PCI device that we've added to a virtual machine, QEMU. This PCI device can draw stuff to the screen. Wow, right? We've implemented a kernel driver that talks to this PCI device and has implemented like a subset of the DRM interface to the point where we can do like pixel by pixel drawing to the screen. We are kind of like on this saga now of trying to implement OpenGL for this card through this library called Mesa. Mesa holds like basically how do I explain this? GPU drivers don't live in the kernel. They kind of do, but they also kind of don't, right? Because GPUs are like high performance devices, and the GPU, like if you were to do everything in the kernel, it would just be too much code in the kernel that is like too rigid and not performant, because every time you have to do anything in the kernel, you have to context switch, right? It would be nice if you could do a lot of the work in user space and just kind of like push things into the device, like basically use the kernel as a way for you to like send data to the device, essentially. So what they have is they have this like DRM subsystem that allows you to extend with like your own commands, right? Then what happens is like you implement the majority of like GPU work in this Mesa driver, and then you just like extend with your own commands, and those commands are like you implement like basically like a backend for your device in Mesa, and he uses, dude, these aren't letters that I can read, but like you guys get the point, is like he knows your GPU specific kernel API that is kind of like minimal, and the most of the heavy work is done in Mesa. That's what we're kind of working on right now. Now we are kind of preparing at this point for like data transfer. So we are going to be working on GPU shaders soon, which means that we are going to have to be able to like upload vertex buffers to the GPU as well as like GPU programs to run. And so we are working today on the idea of like, from user space, can I like mmap a GPU buffer and show some stuff up there? That's kind of what we're working on. Is that still the same paint image you drew like a week ago? I just redraw it all the time. GUSE, GUSE, graphics card in user space. Yeah, that's pretty funny. So that's where we're at. Today, you are seeing us work on like paging, essentially. So we have like this thing where PCI space allows you to export segments of memory, memory mapped sections that basically say like, when I write to this address in memory, it sends this PCI command, I think, something like that. And we are kind of using that to expose a section of memory that like that has like pages, basically, that map to like GPU buffers, right? So we'll have like, you know, buff 1, buff 2, buff 3. And we, from the Linux kernel, can say like, hey, could you put this like this vertex buffer at the vertex buffer's third page? Can you put that in this location in that PCI space? And we were just trying to figure out like what the heuristics should be for like removal and re-adding of those things. And so we think what we're going to do is we are going to basically just make a circular buffer of the most recently mapped piece of memory. And we will just pop the last one and push the latest one. And hopefully that's good enough. It won't be very performant. Especially now people are telling me that DMA should be much faster than you doing what I'm doing. But fuck it. We're already down this road, right? So that's what you're catching in on. I apologize for the kind of scattered explanation, but I think I'm going to have to just keep moving because otherwise all the people here before you guys are going to be bored. But I much appreciate the raid. Thank you so much. Thank you so much. What are you getting from PCI? Like the GPU. We're implementing the GPU as like a PCI device right now. Okay. So where we were at was that we kind of figured that if we were just basically saying the last thing we mapped is, or like, sorry, the thing we mapped, the page we mapped longest ago is the one we don't want, then we can just like basically keep a circular buffer of all of our pages. Then we can just be like, oh, we're out of space, pop the last one, pop it, push in a new one. Easy peasy. I don't really know what lives in this circular buffer right now. I guess if we could just keep this as like the mapped pages, honestly. Yeah, we probably could, huh? So we could just kind of keep this as our buffer, and then we just have like head and tail in here. Yeah. Yeah, that seems reasonable. So these initially are going to be 0, 0. This needs to be sphero bar mappings, and I guess we'll have some function here that's like static sphero bar. Can we make it so that we can just 0 initialize this thing? We can, huh? If we just 0 init this thing, these things will be 0 and we'll be chilling. Okay. So then all we have to do is start like thinking about how we push and pop things. So we'll say, yo, what is the size of this thing? And we're going to take in our like struct sphero bar mappings. Dude, I misspell sphero all the time. I think that it's because the PH are on the right hand and the A is on the left hand. I just somehow managed to get the A down before the PH every time. And this is just going to be head minus tail. Now, you might say, if this is a circular buffer, won't this be wrong? But what we can do is we can allow head. We're going to allow head to be in the range of 0 to 2x size. That's what we're going to allow. And then when we actually index into this thing, we'll just like mod it by the size. And then that way this kind of just works out. I think. Then we're going to have to do some sort of like push. I guess we probably don't even care about the size, really. We probably only care about if it's full. And so here we'll just be like, return this is equal to sphero num bar pages. That seems reasonably. And then we're just going to be like, yo, I'm going to push mapping. Okay. And the push is going to just like say, I am going to write to something. Well, this is not going to handle the case where we're not going to handle like overwriting here. We're just going to be like, we're full. I think that makes sense. So if that's the case, then we can just be like, I guess this needs to take in the mappings. And we're just going to be like, yo, mappings at bar pages at mappings head percent the num bar pages is equal to the page. Yeah. Seems reasonable. And then we move the head. And then we need to say like, I think that's fine. Okay. Then when we pop, we'll call this push head and pop tail. We're gonna do what? I don't know. Why does this return something? It shouldn't. Why does this return a U32? It shouldn't. Okay. So here we're just gonna be like tail plus plus for sure, right? We're gonna go like tail plus plus, and then if tail is gotten too far, let me draw this out real quick. So we're kind of being like, we have some buffer, right? And we're going like head goes here, and Boom, 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 boom. Moves forward, moves forward, moves forward. All the way over to here. Maybe 2 times as far, right? Now we're kind of saying that tail is going to like start here and he's going to catch up, right? So we're going to go like boom, 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 boom as we pop stuff. And eventually we're going to get here. If we get here, then we want to take both of them. Oopsies. We want to take both of them and just kind of like move them back here, right? That's kind of what I'm thinking of. That's what I'm thinking of. So I think we go if mappings tail is greater than or equal to, you know, the size, then mappings tail minus equals this, and the head also goes back down by that much. And then I think that's actually it. I think that's the whole data structure, which is pretty sick. Should you change return type on line 78? I did eventually, but I don't know if you said that before I did it or after I did it. I think this should be a Boolean, but I think you were right. I think you probably said that when it was a U32. Yeah, all right. I guess here we should probably return the page, huh? So we'll be like, ret is equal to mappings data here. Bar pages. Yeah. And then when we use this thing, we can just be like, is it full? If so, okay, I'll pop the tail and unmap it. Otherwise, and then I'll push the head. Yeah, easy. Easy. All right. So that seems actually kind of shockingly straightforward. I kind of thought that was going to be harder. Well, I shouldn't speak before the chickens hatch. What is it called? Don't count your chickens before they hatch? Because it might not fucking work, but it might. Can we actually start with like a number of pages of like 4? Right? That way we can kind of practice usage of this thing and see if it kind of like works okay. Right? So let's do like 496 times 4, something, 4 pages. And we'll just put a fix me on here. Small size for testing. Okay. What is it complaining about here? The array has incomplete type. I guess I did spell Sphero wrong again. It's a hard life out here. And since this thing is 0 initialized into a good initial state, I don't think we actually have to do anything here. I think that when we allocate Sphero priv, we kz allocate, which should make it zeroed out. Yeah, here, kz alloc. So we're fucking chilling there. So that just means that basically in our fault handler, we just need to check this thing. So we're going to be like, are we full? What do we call this thing? Bar mappings full. We do this, essentially. But we need to be careful about what we're doing. So the start is going to be the S doesn't exist here. This is priv is what we called it. And then this wants to be by pointer. If this is full, then we're going to say the Sphero VMA match page to unmap is going to be pop tail. Easy, right? Then here, we're going to look at this thing. So we're going to be like to unmap VMA VM start. Okay. And to unmap VMA. Like, what do I have in here? Oh, no, it's not here. It's a page offset. Here we go. Yeah. I think that's right. That looks right to me. End is equal to the start plus the page size, or to unmap VMA VM end. Okay. That gives us something that we can, then we nuke that thing when we're chilling. Then we do this. So when we insert the page, then we do sphero bar mappings push head into our bar mappings with the inserted page. Okay. Inserted page. And can we do like, how do you do this in this language? You just kind of like do VMA is equal to VMF, VMA. And what was the other thing? Page offset is equal to page offs. And we actually don't need this valid check anymore, actually, because the validness is being tracked by like the circular buffer indices. Cool. Cool. Do you have your new config public? No, I do not. I apologize, but I don't really want to post it, so I get fucked, I guess. All right. That's like a maybe that works. That's maybe that works. Do you have to do anything else? No. All right. Okay. Let's build the kernel, and let's see what happens. I suspect that something will break. Okay, I think I'm in the wrong environment, so hopefully that didn't like fuck anything up majorly. Hopefully. So we'll give it a sec. No, sorry, get fucked, good sir. Yeah, exactly. Sometimes it forces me to like rebuild the whole kernel, even though I'm building this as just like a kernel module. I shouldn't say rebuild the whole kernel, but it likes to like relink VM Linux sometimes, which takes a long time, which is fucking annoying. But it should be on the future builds of this, it should be fine. Should be. All right. Give him a sec. He's still going. Okay, run. Run this thing. So I guess we probably should have added some logs in the kernel, because it's really hard to tell what's going on. But it looks like it's not crashing. Our frame rate's like still small, like low as fuck. That's quite bad. But that's okay. I mean, let's see what happens now. Let's go back into the kernel. Sphero derv. It's already open? All right, I thought it wasn't, but that's cool. Was it, where was I editing the kernel? Okay. Fine, whatever. Okay, what was I doing? I wanted to see what we're mapping and unmapping. So for now, I just want to be like, unmapping, I guess we'll just write like to unmap page offset. And this is a like, surely it's gonna be U32, right? Surely. And then here will be like mapped. Yeah, this is good enough. Okay, so what we should see is we should see a little bit of like a lag here. A little bit of a lag where, since we should have, how many pages do we map here somewhere? We said 4. We should see it like kind of like trail by 4 pages essentially. That would be ideal. That'd be ideal. Okay, run it again. Let's see. Also, I would be curious to see like how slow this is. You know, okay. So this is really, really good. This really looks like our circular buffer is working correctly. Right, so we come here and we see like, we map 0, 1, 2, 3, and the unmap 0, maps 4, unmaps 1, maps 5, unmaps. That's like really, really good for us. And then we can go here and we can see that he is in fact still doing something. Now, it's slow as shit still, but we'll get there. Okay. So can we just like crank up this thing to... I think we made a mistake in the QEMU side last time and we never fixed it. where the PCI bar size was too small. Yeah, here. This needs to be like this for 256 megabytes of PCI bar space for us to work with. And then here, can we do 256 times 1024 times 2024 here as well? Okay, let's see what happens if we do that. Okay, I think we're gonna chillin'. Let's see if that's any faster, because what we should see now is that it should map the buffers once at the beginning and then just be fine. That's what we should see. Now, we probably won't because, we never do anything right, but maybe. We could dream. You also had your pages stuff in QEMU at 64 pages and 64 times 1024. I think that's 64. Oh, yeah, that's a good point. Why did I do that? Then this needs to get like shifted right. Divided by 496. I guess is kind of what we want. Fix me where the F should this be? Definitely should be named. Defs should be a named number. Defs should be deduped with bar mapping. All right. Good eye. Did you just remember that from the other day, or did you just see it while we were skimming by? Because either way, good fucking eye. All right, let's fucking run and see what happens. So again, we are expecting to see one set of mapping up front for however much memory we're using, and then nothing. Oh, maybe we removed the map logs. Also, this looks broken as fuck. Okay. Interesting. Interesting. We've regressed for sure. Can we look at fault? Okay, let's log maps and unmaps again. So I'll just write it again. Fuck it. Unmapping page offs this, and wherever the fuck we were here, mapping page offsets page offs. I'm hoping to see that this is not really used that much. You did the whole 256 megabytes over 496K and ended up with 64. Oops. Oopies. Should be over 496, not over 496K, but I get what you mean. I think that was probably my mistake, actually. All right. Root test app dev dri card1. Yeah, okay, so that's really good. We do see it just like ripping through mappings up front. And he is mapping page offsets for multiple buffers. Hopefully these are multiple buffers with different GPU IDs or different like hardware IDs. Now, this is concerning though. This is concerning. Why did it work before but it doesn't work now? Would it be nice if there was some way undoing only that you have selected? Yeah, that'd be kind of cool. This is very interesting. This is kind of like back to where we were the other day, but I think just because like of a completely different root problem. I'm trying to guess what I think that problem is. So we can still see, by the way, that the frame rate's really low. It's probably because every single PCI memory rate is going through like this like slow function in QEMU that we implemented. But it might be worth starting to log our writes in here. So can we go like... Let me think about this. We are trying to draw a smiley face, right? And the smiley face is supposed to be He's supposed to be yellow and black. And can we like detect that from here? What's like the size of our right here? I'm actually not sure. Let's start there. Because if our right size is like 8 bytes, then that's like going to be kind of annoying. If it's 32, or sorry, 1 byte is going to be annoying. If it's 32, it's going to be a little more. I'm trying really hard to chill for Linux, but sometimes I feel superb tooling. Sometimes I miss the superb tooling of Visual Studio. It feels bad. I don't know, man. I was never a big fan of Visual Studio. It's like okay. It never really like felt like it really was like miles ahead of anything else. I don't know. Visual Studio Code's pretty good. Pretty decent. I don't really know what else you're looking for. Okay, so we are writing 4 bytes at a time. Okay. And how is that working in our test application? So really these writes should be coming directly from user space. Right? So I guess we have to do that in this terminal window. So we're kind of doing this like draw smile thing, and we are doing like draw rectangles. Okay. Draw rectangles are writing data, which is a U32. I see. So it looks like we can probably identify the colors that are being written. I think we can probably identify that. So in here, can we like look at what we're writing? So can we, it would be nice to like keep a tally somewhere. So let's do like, when we will count like num yellow pixels and num black pixels. And when we put the frame buffer, we will clear those things. Okay. So every frame we reset them essentially. And then when we write, we will just check. So we'll say like, if data and mask is equal to I don't know. Maybe we just start by printing out the data here, and we'll kind of move on from there. Can we just do like printf data is the data and the mask. Oopsies. %x data and mask. Okay, let's just, this is gonna spam the fuck out of us, but I don't care right now. I'm just trying to get a feel. Get a feel. Oh, he doesn't like that because he needs to be an LX, I guess. It's fucking annoying. And can I say that I want this to be like, oh fuck it. I was gonna say like I wanna make it like the same amount of bits or the same length every time, but I don't really want to remember the printf formatting string for that. It's like some like 0 prefix something something. I don't care. I don't care. All right, let's see it. Root test app dev dri card 1. Okay, so yellow is 00ff00, and then it looks like black is full 0. So it looks like the alpha channel is unused. So we want to do this. Okay. S num yellow plus equals 1. And then we go else if data and mask is equal to 0. This is black. And then we should probably do else other, which shouldn't happen. Okay. And then we do here And then here we can print num black, yellow, other. And these should be like used probably, right? Okay. So this should give us a clue about if the writes are actually making it to the virtual machine. Let's see. Okay, root test app dev dri card1. That right size 4 spam is going to get really fucking annoying. Oops, didn't mean to leave that in. It's a hard life out here. It's a hard life. For us, it's a hard knock life. For us. And let's check again. Please give me what I want. Why am I not seeing that log? The fuck? Oh, I fucking put it in the wrong spot. God damn it. It's the other. There's multiple places where we do this, like, graphics update, and I just put it in the wrong spot. Oops. Oopsies, 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 oopies. Alright. Run. Run, run, run. If only I didn't have to wait, like, 6 seconds every time. I know it doesn't really matter, but it's annoying. Okay. So it looks like, I forgot a new line, but we are kind of seeing the correct behavior here in that we are writing the right amount, right? We're writing like the right thing. However, we are not seeing any black pixels show up here. So I think the next interesting thing to look at would probably be where are the black pixels getting written? I mean, we can probably assume that this is something to do with the mappings being wrong, right? Probably what's happening is we are writing to the... Well, the black writes should all come after, right? The way that the like user space code is written is we render the for the whole buffer as yellow, then we draw the eyes and the mouth. So it looks like the black pixels must be getting written to like completely to the wrong buffer. That would be my guess. Is there a black stripe at the bottom, or am I drunk? That's a good question. You know what? I'm down to check that. It's like really fucking hard to see from Twitch chat, I would guess, because of like encoding. I don't think it's a black stripe, but I do see something there. Can we, right? There's definitely something there. Very interesting. And I would bet, 1024 times 768. Well, 1024 is like the width of our frame buffer times 4. So if there was something wrong, it would be like it would be line aligned, right? Each page is one line on X. So here we're kind of seeing this could be where his mouth is supposed to be. It could be. Right? Because the user space app does calculate the mouth. I width is the width over 10. Left center X, Y center X. Left center X, right center X. Oh, he just goes for like the whole eye. Yeah, so the eyes are like at approximately 1/3 to 2/3. So could be that we're seeing like something to do with the mouth down there. That seems very possible. Now we should assume that it has to do with our page mappings, right? So maybe what we should do is dump the page mappings, or maybe try to, yeah, let's dump the page mappings as well as the frequency that they were written to. I like that. So we'll do something that's like num. We need to keep track of the num pages mapped just for now. So every time we insert into this pages array, we're gonna say s num pages mapped plus equals 1. I guess we should probably try to oh wait, hold on. In the kernel, I think I just realized something. I think I'm a dumbass. I think we're seeing the same behavior of that like giant white yellow screen because we're doing the same fucking bug that we were doing before. Just page num 0. Fuck. We're so stupid. Okay, so what we actually need here is probably like the head pointer of our mapping buffer. Of our like, this should be like sphere, the, what is it? Priv? Mapped GPU bar mappings? Head. I'm pretty sure it's this, right? Because the head is working in a circular buffer, but the mappings are in bar mapping space. Bar page space. So I think this is right. Dude, I swear to God, if you're saying, I want to share good news, who wants to hear it? I swear, if you're another one of these fucking people who's coming into a programming stream to spread their religion, I'm gonna lose my shit. But if your good news is like, I got hired at Google, that's like relevant and exciting, you could share that. But I swear to God, if you open that present box that you put on the screen and it's religious, you're banned. Okay? Perfect. Moving on. Okay. Build Linux. Are you just testing if I'm gonna ban you? Someone else just comes in and is like, I found God. I don't care. I don't do it. I mean, I think he's joking, which makes the ban a little bit hard. But we'll see. If you guys, I guess I have to set a precedent because now if you guys start spamming it, then it's gonna be like fucking annoying. Oh, he said I was joking. Thanks, Ann. Okay, woo. Okay, we're outie. Okay, no more. Make an example. Ban him. Okay. Let's go back to writing code. Okay. Test app dev dri card1. And let's see if this looks more sane now. We're so back, baby. We're so back. Okay, so it's absolutely like slow as shit. Like slow as shit. However, I actually don't know if that's like wrong, right? Like this is kind of just like whoever said, I think it was XX the big fox X, was saying that like we don't have to like eat PCI transmission cost in the case where we're doing like direct reading from memory from the PCI side. Now, I didn't consider the fact that the PCI communication cost in a virtual machine is going to be like fucking massive, right? Because every time we write a pixel from user space now, every single pixel that is being written goes through this callback, which does like debug code. So it's kind of shit. I wonder if this, like, on the QEMU side, I wonder if on the QEMU side we can do something more sane. Right? We have memory region init IO, but are there like other examples? Could we just like fucking hook it up to a buffer? Oh, but we can't even hook it up to a buffer because the whole point of this is that we're doing lookups, which just means that this has to be slow. Right? Unless we could kind of like batch the write as like a full page at once, which I just don't know if is possible with the way this is set up. So this might just be a bad idea. Which is kind of funny. Which is kind of funny for sure. Let me think just a little bit more. So this like memory region IO thing would be the case. Forgive me if this is obviously wrong, but thinking of Doom, everything was deterministic. Okay. I don't really know what you're asking. I think this wouldn't be super slow on hardware, but in QEMU it's gonna be awfully slow. Yeah, I think that is true. Now the question is do I care? Right? That's what I'm trying to decide right now. Is like, we could go through the work of fixing this, right? And even then, I think we saw somewhere in like Linux GPU driver guide. I think we saw something about like mmap in here. No, could have sworn. I thought it was in here. Oh, is this just the table of contents? Can I get it on like one page? Driver initialization, memory management, it's probably in here. I think we read in here that like it's like fucking slow and like people don't actually do this. I saw something like bulk transfers. No. All right. Well, I think I read somewhere that like even though we could do this, like this mapping of GPU memory directly to user space, people don't actually do it in the real world because the page fault, even if the PCI part wasn't slow, just like having to fault all the time in order to map the memory is kind of like noticeably slow. So I'm not sure. I think that like that it is working though, right? And if this is supposed to be our like our way of transferring GPU like programs and what's the other thing? Programs and vertex buffers, we could maybe just kind of leave this as our scheme for now, which will be slow as shit, but also not that bad, right? The reason it's so bad right now is we're transferring a full frame of data every single frame, and it's just like a fucking course, and we're not even like doing it, we're writing it like pixel by pixel, right? Which is like super slow. So I guess what we could do is we could add a command to like write a full buffer. No, anything we do, I was gonna say we could like do this all in one syscall or something, but it would still be slow because the slow part is QEMU. Okay. I thought this would take a little longer to get to the point where it worked. We did kind of get there. I think that I am coming to the conclusion that I think that this is a bad system. However, maybe it is somewhat reasonable anyways. Probably what makes sense is to go back to the frame buffer being transferred through shared memory. It probably also makes sense to do vertex buffer transfers through shared memory later, but I will think about it. I think I'm happy with the progress. Whether or not the idea was good or bad, I think I am pleased that we got to the point where it works. So I'll brainstorm, I'll think about it. We're ending, I think we'll end a little early today. I thought this would be harder. It is 3:20. We usually try to go till 4 o'clock, but we will live. I will use the next 40 minutes, or like the extra 40 minutes, to do more reading about GPU shaders. So, thank you for watching, you guys. Thank you, Bash Bunny, again for the raid. We have a lot of extra viewers here today. If you're new here, we have a YouTube link in the Twitch description where we have playlists for all of our previous projects. We're working on this idea of like building towards making a GPU at some point. But you know, there's other stuff back here if you want to check it out, like a QR code decoder, an operating system, like a video editor, like this like Maps app. There's lots of stuff in there if you want to go check that out. We stream most days 12:30 to 4 o'clock Pacific time. So if you want to swing back by, 12:30 to 2 is usually like a kind of like a casual, more casual, less like new featurey type shit, and it's more like laid back and I don't know, what do we do? We like do like refactoring and like we try to like basically prep for things or clean up our messes, right? So we like leave a lot of garbage around in these like prototype streams and we clean those up and put them into like proper shit, right? Tests, read, you know, whatever. 2 to 4 is what you're seeing now. What else? Tomorrow we'll be working on GPU shaders, so swing back by if you want to see that. In Mesa, they have some calls that we've kind of stubbed out to the point where we can like execute the OpenGL calls to say like make a triangle with these vertex buffer or with these vertices and draw that triangle on the screen, but it does nothing. So we're gonna have to start looking into what does it look like to take like Mesa shader intermediate representation, turn that into something that like we can execute on our fake GPU. So that's what we'll be working on tomorrow. So swing back by tomorrow too if you want to see that. Otherwise, I think we say goodbye to YouTube and Twitch. Let's find someone to raid.